Professor Tarashankar Debroy. He was born in India, graduated from Durgapur Regional Engineering College, and completed his PhD from the Indian Institute of Science, Bangalore. He did his postdoctoral work at Imperial College and at MIT, and is now a professor of material science and engineering at the Pennsylvania State University. Professor Debroy has published extensively on additive manufacturing, welding, and heat transfer. For his research, he received many Best Paper Awards and Fellow and Honorary Membership Awards from the leading professional societies. He served as Fulbright Distinguished Chair in Brazil, Distinguished Visiting Professor at IIT Bombay, and the Aditya Birla Chair at the Indian Institute of Science, Bangalore. Professor Debroy was awarded the Arata Award of the International Institute of Welding, France, Penn State's highest award for scholarship, the Faculty Scholar Medal, and the UK Royal Academy of Engineering's Distinguished Visiting Fellowship. Professor Debroy is a founding editor of the Science and Technology of Welding and Joining journal. His book on innovation in everyday engineering materials that he co-authored with Professor Harry Badeshia has been published last year by Springer. And what we have done, we also got copies of your book at our Knowledge Center. Today, Professor Debroy will speak on innovations in engineering materials powered by the digital revolution. So thank you, Professor Debroy, for accepting our invite. I'll hand over the stage to you.
Thank you very much for inviting me. This invitation means a lot to me because, as you said, I went to school in Durgapur and Bangalore. I want to talk about innovations in engineering materials and how the digital revolution is changing the way we viewed innovation in the past. For all of us to be on the same page, I want to share with you what I have planned for my precious 25 minutes. I want to start with a remarkable innovation in stainless steel making and see what we can learn from that experience. This would be followed by another equally astounding invention at TWI in UK, not too far from Cambridge University, in which metals can be welded without forming a single drop of liquid or any fumes at all. And then I want to talk a little bit about what we work on, that is 3D printing or additive manufacturing, and what we can learn from that in terms of the innovation. Finally, I cannot overlook that this is a talk in which many of the interested people are in the sector of automotive and farm equipment. So I want to talk a little bit about some work we did for Caterpillar and what we have learned from those types of work, and specifically emphasizing how the digital technology is radically changing the way we answer important questions of industry, and also how we solve problems, day-to-day problems. And finally, what about the innovations of the future? How they are going to be helped by the emerging digital tools? I want to start with a remarkable innovation in stainless steel industry. Traditionally, we made stainless steels in the electric furnace, and we always start with a melt containing iron, nickel, chromium, and carbon. Making of stainless steel requires reduction of carbon content by oxidation. We blow room full of oxygen per minute and we oxidize carbon in the melt. But the problem here that one encounters is that when we try to oxidize carbon, we also oxidize chromium. So in order to avoid the oxidation of chromium, we first of all oxidize carbon, lower the carbon content to our desired level, and then add ferrochrome. Ferrochrome costs about $1 a pound, low carbon variety. We cannot use the high carbon variety of ferrochrome that costs much lower, 50 cents per pound of chromium, because if we add higher carbon containing material and we try to oxidize that, we will oxidize chromium as well. So selective oxidation of carbon is not possible in electric furnace. That was the problem. Now I switch gear and you have the context. I want to take you to a story of a fresh graduate obtaining his doctorate and joining the Union Carbide Company in Niagara Falls, a city most people visit for a very different purpose. You know what that is. But Krivitsky, the young engineer, 27 years old, was doing experiments using iron carbon chromium melts that he was oxidizing with pure oxygen. The purpose was to create thermodynamic data in the iron carbon chromium system. So he found after one or two experiments that the temperature of the bath was shooting up to about 3000 degree Fahrenheit because of exothermic heat. So what he thought is that this is not acceptable. He needs to maintain the temperature to a constant lower value. So he thought he would reduce the oxidation rate. After all, rate has nothing to do with the thermodynamic equilibrium. So he diluted the oxygen with argon, and he expected that the rate of reaction will be lower, and so he will be able to do isothermal experiments at lower temperature. He did a couple of those experiments, and to his surprise, he found that the carbon content was very low, lower than 0.01 weight%. And the temperature was lower, but chromium was not oxidized. So he thought that he has found a key for selective oxidation of carbon in an iron carbon chromium melt. And when he reported this to his superiors at Niagara Falls Union Carbide office, they were excited because this can then serve as a basis for creating a radically innovative stainless steel making process in which they will be able to use high carbon forms of chromium. Union Carbide was not a stainless steel maker, so they contacted a stainless steel manufacturer in Fort Wayne, Indiana, and they took about 5 years to figure out how to scale this thing up. By that time, Krivitsky left Union Carbide. He became a chief technology officer in Beryllium Company of America in Pennsylvania. It took 5 years for the Jocelyn Stainless Steel working with Union Carbide because they had to overcome many difficulties. But they did not give up. 5 years is a long time to support financially a large-scale trial and error testing. But after that, there was a big prize. It was so big that by 2000, more than 100 companies adopted that technology. Today, practically all of the stainless steel makers use this technology. So this was a radical innovation in a basic industry like no other. What was the underlying science behind that? You see, what I am showing to my left is a typical steel making converter. And people inject oxygen and argon through the lower end through what we call tuyers. And as soon as oxygen gets in contact with the iron, carbon, chromium, nickel melt, they form oxides of those elements. They are lighter than the metallic melt, and at that time, chromium oxide gets reduced by the carbon in the melt to form chromium. So we don't lose chromium as chromium oxide anymore, but we recover almost all of the chromium in the bath. So we can selectively oxidize carbon without oxidizing chromium. And this is the ultimate in stainless steel manufacturing. And carbon monoxide gets diluted with argon gas. So because the partial pressure of carbon monoxide is reduced, the forward reaction goes at a very high rate and we recover all the chromium. Remember that high carbon ferrochrome can now be added because we can oxidize carbon without oxidizing chromium. And the difference in the price of chromium in the high carbon variety of chromium and low carbon variety of chromium is 50 cents a pound. A 100-ton heat containing 18% chromium will have 36,000 pounds of chromium. So for every heat that takes less than half an hour, a company adopting this technology will save 18,000 US dollars per heat. And also they will be able to make extra low carbon variety of stainless steel. So two huge benefits, humongous cost saving and big quality improvement. Now, what made this innovation possible? Of course, Krivitsky expected to write papers, technical papers, but his research did not end up in equations, charts, and research papers. It ended up something that was very radical in the stainless steel industry that touches the lives of all people in the world. And this disrupted technology, of course, started with the spark of an idea, but it didn't stop there. There were lots of hurdles, and it took about 13 years total, in which nobody gave up, particularly the corporate R&D. They supported him and they supported other subsidiaries to make this innovation possible. I want to change gear and I want to move to another innovation that is equally astounding. This is Dr. Wayne Thomas in TWI, which is a research organization for welding. And he was playing with friction welding, and he found that sometimes it is very easy to generate a lot of heat without melting the materials that we were supposed to join. And it works like this. There is a tool with a large shoulder and a tool pin. The tool rotates at a high speed with large amount of friction between the tool shoulder and the material here. And as a result, we generate a ton of heat so that we get white hot temperature at the tool, but no melting, no fumes. The metal is plasticized. It moves to the rear end of the tool as the tool moves forward and is joined. Now, most of the work was done on aluminum alloys, and today, world's largest robotic friction stir welding machine stands tall, 52-meter tall, in New Orleans, and you are seeing a facility that is owned by NASA that makes the world's most powerful rockets. And you are seeing the picture of a liquid hydrogen tank that can hold about 537,000 gallons of liquid hydrogen. So this is a very critical application, but NASA uses this technology, friction stir welding technology, for their rocket engines. Here is a senior scientist talking to his grandchild, and he says, this part can only be made by friction star welding. And the grandkid asks, no melting, no fumes, no sparks flying. Is this really welding? This is pushing the limits of technology. Can we weld everything? Of course not. We can right now weld very ductile alloys like aluminum alloys, but we are trying to make this thing possible for other materials like steels. So what happens when we try to do that for steels? Somebody has an idea and the perseverance to make this demonstration and show that it is economically very attractive to weld aluminum alloys, particularly for automotive and farm equipment sectors. Here is the problem. The senior engineer goes to the CEO and says, we could weld aluminum alloys very well, but when we try to do this for steel, we have got huge problem. The tools endure a lot and ultimately they break. At what cost? $150 a weld? No, that is too much. And the CEO is stressed out. And so it falls on researchers to find a solution. And one of the tools that we have developed in the last 20 years or so is to simulate. Do the work in a computer before you actually weld the stuff, because then you can learn what the outcome is going to be. If you don't like the outcome, you change your parameters. You can test out numerous different scenarios before you spend money and time. This opportunity was not there before. So I want to show you what the simulation looks like. Here is a simulation. Here is the tool right in the middle where the arrow is. It is generating heat, and the colors in different locations indicate temperature. And we can also calculate the stresses on the tool, the torque, and so we know the outcome before we actually do a single experiment. This opportunity was not there before the computations became inexpensive. A $600 laptop can simulate the process in less than half an hour. So I want to change gear again, and I want to take you to a radical innovation that took over 20 years to mature. And things that seemed to be impossible just a few years ago can now be made. So what happens here? We make 3D parts, one thin layer at a time. How thin? Sometimes thinner than a human hair. So here is a powder bed fusion process in which we can make complicated shapes. We can make site-specific chemical composition of a material, and we can make stuff that has internal cooling channels, very attractive for automotive and farm equipment sector. And most important, the same equipment can produce today one component, tomorrow if there is a need for making another component, that can be made as well. So what happens is we spread a thin layer of metal using a roller and then use a heat source, in this case a laser beam, and we melt selected areas, this layer, and then we spread another layer and do the same thing, and we progressively deposit many thin layers to make a 3D component. In this case, I am showing a Nittany lion, our mascot for Penn State, being made by the powder bed fusion process. There are other varieties of additive manufacturing called directed energy deposition using a laser beam or an electron beam, or directed energy deposition using an inexpensive gas metal arc heat source. So what are the unique advantages of this type of deposition? General Electric, the largest manufacturer of jet engines, uses a factory in Alabama to make fuel nozzles. Fuel nozzles used to be made by assembling 21 parts, and today it can be made as a single part, and it increases the reliability of jet engines. We can make compositionally graded materials. For example, here we have chromium molybdenum steel joined with a nickel alloy 800H. This joint of dissimilar metals is a common thing in nuclear power industry. And we did some research to show that if we can avoid this dissimilar metal joint that has severe creep problem after about 30 years, and replace that dissimilar metal joint by a graded joint in which the composition changes gradually, we can increase the creep life by many, many decades. One last example, the International Space Station had a message for NASA that we need a ratcheting range, and NASA had no resupply mission planned. So what NASA did was they sent a design of a 3D printing of socket range to the space station from the Earth for the desktop printer inside the space station. So they remotely printed a ratchet in 104 layers of plastic at the space station, and all the commander had to do is open the drawer and pick it up. That's it. So what do we make today? Starting from pulley to a hip joint, to gas turbine blades, to fuel nozzle, to hydraulic valves, to customized bottle opener. Everything can be made. But does that mean that the innovation has stopped after we have devised a way to make it? Not really, because how many commercial alloys are there? Over 5,000, right? So of those 5,000 alloys, we can now print only about a handful, maybe 10 to 20 alloys. Other 4,980 alloys cannot be printed. But there is hope. There is hope because we have rich and mature knowledge base of metallurgy. We have the emerging digital tools, and we have lots of small and medium-sized businesses that are eager to play in this market. But they have to solve many defects such as cracking, surface roughness, lack of fusion, porosity, a ton of other problems. And not least, cost competitiveness. Products have to be such that market can bear its cost. But here there is an opportunity roadmap. The roadmap is to integrate the emerging digital technology with the existing hardware that will give us rapid solution so that it doesn't take 13 years that it took for the stainless steel to develop. And most important, these will be based on scientific principles, not trial and error, cut and section and try it out, using mechanistic models, machine learning, and ultimately digital twins. General Electric has 5,500 digital twins. Siemens has thousands of digital twins. So this is an opportunity roadmap. Please ask if you can take advantage of the most modern science-based tools rather than do and see. I want to tell you about the application of digital technology, some work we did for Caterpillar, and they make a lot of earth-moving equipment. If you section a weld, you can see all of these. How do you know what is happening in the interior of the material that you are trying to join? And why is this important? You have to ask, if you are an engineer, how is this material going to fail? If it fails, God forbid. And the answer is very simple. Most of them fail by fatigue. And so you have to increase in your design fatigue strength if you are doing welding. I want to show you a simulation. So you see the heat source is moving, it's pushing the liquid backwards, and it's forming a shape, a weld bead, if you will. And the key to increasing the fatigue life in automotive and farm sectors is to have the right bead, because that will give you 1,000 years of fatigue life. Okay? And you want your quality to be very good. So here is a weld, gas metal arc weld, and you see this dome here. This contact angle decides whether this edge is sharp or not. If you have a very sharp edge, then the fatigue life would be lower because a crack can initiate and propagate. So improper parameters will give us poor geometry, poor mechanical properties, and God forbid, catastrophic failure. How do you increase fatigue life for this material? You decrease your angle theta. Basically, you change the toe angle and the reinforcement height. That is exactly what we did. We did simulation and we showed that before they do the welding, we can tell them what's going to happen if they did the welding. And they wanted to test us, so they did lots of experiments. And each case, here are the results. So simulation is trustworthy, it is better than trial and error, and it can be relied upon. And most important, you are taking advantage of all the scientific knowledge in the form of a virtual welding. Virtual welding before you do the actual welding. And this is a pictorial view that this can be done. And not only that, you order your materials from a supplier. Say you order a steel, and within the category of steel, at different times, they may give you steels that comply with the standard, but has very little difference in surface active elements. Like in this case, 20 parts per million of sulfur, very, very insignificant, and 150 parts per million of sulfur. And look at the difference in the shape. Look at the penetration depth on the right versus the left. And why is this happening? If you also do simulation, apart from doing experiments, you will know the reason. The flow pattern changes. When it has little more sulfur, the pool is deeper because it acts as a thermal drill. When the sulfur content is very low, the liquid moves from the middle to the sideways, so the shape is wide and shallow. And you can do as many experiments as you want, but you will not know the reason. You will know what happens, but you will not know why. And in innovation, many of the whys are as important as whats, if you want to make use of the scientific knowledge. So simulation is scientific knowledge in digital form. My final comment, innovations of the future. How can you make a culture in which innovation is promoted, and is promoted not by the elites, it's promoted by everyone that wants to do it. So that it does not matter if you do your experiments in Bangladesh or Bangalore or Abuja, Nigeria, or Stockholm, Sweden, or University Park in Pennsylvania, where our offices are, and we do simulation all the time. Critical problems in manufacturing are solved by time-consuming and expensive trial and error, do and see, and make parts and test it. So you need expensive equipment, you need a big laboratory, and it is time-consuming and expensive. And there is an opportunity roadmap here. Use modeling and machine learning without any empirical testing initially, and optimize your parameters, and use this scientific knowledge. Use the spark of your imagination that has no substitute, but also use this science. And what will happen? You will improve the quality without trial and error, and then make a few tests to verify your predictions. So there will be fewer defects. You can test out different materials without doing experiments or without ordering new materials from your suppliers and paying for it. So it'll be cheaper, it'll be based on scientific knowledge, and your products will be certified much quicker. This new path will allow your technology to mature quicker. You will not need big test facility, you will not need specialized equipment, and most important, everyone with a $600 laptop can participate. So you will enable and empower all your employees that want to do it. Ideas will be valued and not the attributes that divide us, because everyone will be able to participate. So race, religion, ethnicity, nationality, affluence will not matter. Researchers without expensive facilities can contribute, and this will make the world a more inclusive place. When you empower people, you promote innovation. When you make people valuable and listen to them, everyone benefits. All people in the world will benefit in this paradigm. And more of our work in our website, our LinkedIn posts, and in the YouTube. Thank you very much.